Hi, this is Pratik and welcome to Code Verify. In this video lesson, we'll learn about converting a binary tree to a threaded binary tree. Now, the reason behind converting a binary tree to a threaded binary tree is in-order traversal. That is, this conversion will allow us to do in-order traversal without using stack and without using recursion. And this would make the in-order traversal really simple and fast. Now let's understand how to do this conversion, and in the later upcoming video I will show you how to do in-order traversal of the threaded binary tree. Now let's suppose that this is the binary tree that is given to us and we need to convert this binary tree to threaded binary tree. Now its corresponding threaded binary tree would look something like this. And here you can see that all those nodes which did not have a write connection, they all got threaded to the in-order successor. Now by the term in-order successor, I mean that if you traverse this binary tree in an in-ordered manner and you store the in-order traverse node in a queue, then the queue is going to hold the nodes 4762513. Now the term in-order successor means that node 7 is the in-order successor of 4. Which means for a node, its in-order successor is the node which is present at the right side in this queue. So similarly for node 7, its in-order successor is node 6. For node 2, its in-order successor is node 5, and so on. So in this binary tree, if you look at all those nodes which did not have a write part, for those nodes they got threaded to the in-order successor. Like 7 did not have a write part here, so 7 got threaded to its in-order successor 6. Similarly 6 also did not have a write part, so 6 also got threaded to its in-order successor, that is 2. And similarly 5 also got threaded to 1, which is 5's in-order successor. And also remember that the reason I am saying that this is a queue is because we're going to perform queue operations here. That is, the insertion in this queue is in the right side, and we will be popping from this queue and we will be popping from the opposite side. So remember that in a queue, the insertion and removal of elements happen from the opposite side. So the first step would be to build a queue containing all the in-order traverse nodes. And the second step would be to get all those nodes which do not have a write part and connect those nodes to their in-order successor. Now let's perform the first step, that is, we built a queue. So to begin with, let's make a class node and define a constructor. And we're going to pass the node data here, that is the node data which is going to be present in the data part of the node while we make the structure of the node. So now we're going to make the structure of the node, that is, first will be the data part, and second will be the write part, and the third will be the left part. So the first is the data part, and that will contain the node data. The second part will be the write part, and that will be none, because initially when a node is built, its right and left are none, and similarly its left is also none. So now let's build the binary tree first, which we want to traverse and build the in-order traverse list. So I make an object of the class node and I pass the node data 1, signifying the root of the binary tree will be in the node with the data as 1. And similarly I make the other connections, that is, I build the left of this root, that is the node with the data as 2, and I'm going to make the other connections in the same fashion, so that our final binary tree would look exactly as I have shown you in the example. So now it's time to build the queue. So I'm going to name a function called inOrderQueue, and this is going to make the queue which is required for this operation. And in this function I'm going to pass the root of the binary tree, with the help of which I'm going to make the queue. Now, to build the in-order queue, you have to do in-order traversal first. So first I'm going to check if the root passed is a valid one, that is, it is not none. Then now I'm going to recursively call the inOrderQueue function again, because remember that in this queue the first element is 4, which means we have to reach out to this 4 node. And that we can do by recursively calling the inOrderQueue function and passing the root.left as the parameter, which means the code will keep on traversing leftwards until it reaches force left is none. So until it reaches none, it will keep on going downward in the left direction. So I'm going to write here inner q root dot left, and finally it will reach none because force left is none. So when it reaches none, this function will again run and it will check if root. Now root becomes none, which means the entire function will get over without doing anything, and it will return to its previous function. So I hope you are able to visualize this, because this is a recursive function and it will be like a function built within a function. So if I build the structure for you, then the first time the function in order q runs, it contains the parameter roots, that is node number 1, that is the root. And now we are calling this function recursively, that is a function will be built within the uppermost function, and this time the parameter passed to this innermost function will be the node with data as 2. Similarly, again the function gets called within itself, and this time the parameter is the node with data as 4. Now again the function is called recursively, and this time the parameter is none because force left is none. And when this happens, this condition gets violated, that is root becomes none, which means it's not going to call again itself recursively, which means this innermost function gets executed without doing anything. So it's going to simply return its authority to its upper caller function. Now in this upper caller function, which is having the parameter with the node with data as 4, I need to take this node and put it inside the queue. I'm going to define the queue in the main, and the queue will be initially empty, and we're going to use this queue which is declared globally, and we're going to use this queue inside this function. So initially the queue is empty and we need to append the root with data as 4 inside the queue. So when we are at this function with parameter as the node with data as 4, and at that function I am gonna write q.append root, which means the node with the data as 4 gets appended inside the empty queue. And after doing this, we need to go to 7 and append this inside this queue, which means I will definitely have to go to the right of 4. The right of 4 is this subtree, and upon reaching the subtree I have to go to the leftmost element of the subtree in order to get hold of 7. So I am again going to make a recursive call, and this time pass the roots right as the parameter, which means now the parameter is the node with data as 6. It gets passed as the parameter to this function, which means now in this newly called function with the parameter as node with data as 6 runs from the beginning, and it's gonna check if root, yes, root is not none, which means all these steps will have to get executed. So first it again gonna call itself recursively, and this time it's gonna pass root dot left, that is the node with data 7 as the parameter. Now the story is same, again it's gonna call itself recursively, and this time pass none as the parameter. And when this happens, it will again gonna give its authority back to its upper caller function. And when we get back to this upper caller function with the parameter as the node with data as 7, and in this function the second line runs, that is it's gonna append 7 inside this queue. And after the appending is done, the third line gets run, and the third line is this. It's again going to recursively call itself. Let's show you the recursive call. So here it is. You can see that none is passed as the parameter in this recursive call because 7's right is none. And when this happens, you know the consequence, that is it's going to return its authority back to its upper caller function. And back to this upper caller function, it sees that it has executed all the 3 lines under it, and which means it is done with itself, and it's going to return its authority back to its upper caller function. And now in this upper caller function, it sees that it has executed its left part, which means now it's time to append itself inside the queue. And after the appending is complete, this function runs its third line, that is it will deal with its right part. Now again 6 right is none, which means whatever happened with 7 will happen with 6 also, and it will again call a function with parameter as none, and that is again going to return the authority back to this function, and this function will also get executed in the same way 7 got executed. And after this function gets executed, it's going to return its authority back to its upper caller function, which is this. So in this upper caller function with parameter as the node with data as 4, it sees that it has executed its left part, it has appended itself, and it has also executed its right part, which means it has also executed all the 3 lines of code. So it will again going to return its authority back to its upper caller function. Now in this upper caller function with node as data 2, it has already executed its first line, that is this line, and now it's time to append itself inside the queue. So 2 gets appended inside the queue, and after the appending is done, it runs the third line, that is it recursively calls itself and passes 2's right as the parameter. That is, the function will have a parameter with the node with data as 5. So when this function runs, it runs from the beginning and it again wants to go to its leftmost part, but its leftmost part is none. Even if the function gets called, its parameter will be none, which means if that function runs, it's gonna return the authority back to this function itself. Alright, so again in this function, the second line of the code runs and 5 gets appended inside this queue. And after this, the third line runs, that is it's gonna recursively call itself and pass 5's right as a parameter. So again that function runs. You can imagine it for yourself, I'm not drawing it here. So when that function runs, none is passed as the parameter to that function, and the story is same. Whenever none is passed as a parameter, it's not going to do anything, it's just going to return the authority back to its upper call function. In this case, the upper call function would be the node with the function with parameter as the node with data as 5. So back to this upper call function, sees that it has executed all the 3 lines of code, which means it is over, and it's going to return its authority back to its upper call function, which is this. So when we are back to here, it sees that it has also executed its left part, it has appended itself, and it has executed its right part, which means it is also done with itself, and now it's going to return its authority back to its upper call function. Now back to this uppermost function, it sees that it has executed its left part. Now it's time to append itself inside the queue. So 1 gets appended. Similarly, it's gonna call its right part the same way this function called its right part. So this function is also gonna call its right part. The story is same, and when this function runs, it's gonna run its first line of code, that is its left part, and that when that function runs, it's gonna pass none as the parameter, which means the execution of the authority will return back to this function, and now it's gonna append itself inside the queue. And similarly, its right part is also going to run, and also in its right part, none is gonna be passed as the parameter. And again, the authority comes back to here. It sees that it has done with itself, and it again returns its authority back to its upper caller function. Now in this upper caller function, it sees that it has executed all the 3 steps, which means it is also finally over, which means we are done with the entire function execution, and we have finally got the in-order queue that we needed to do the threading. So now we have got the in-order queue that we needed. So after this, we're gonna make the conversion, and for that purpose I am going to define a function convert, and this is going to take the root as the parameter, that is the root of the binary tree. We're going to take the root and we're going to use that root to get the threaded binary tree. Now to do the threading, you're going to start from the bottom and move to the top. Let's see, if you're going to start from the bottom, you're going to first thread 7 to its in-order successor 6. So to reach 7, you have to reach 4 by recursively calling the left part from the root. So the first destination is this. Once you reach here, you're gonna grab hold of the right subtree, and you're gonna do the same thing. That is, you're gonna recursively roll back in the left direction, and you're gonna reach 7. So this is the second destination, and upon reaching 7, when you cannot further roll back, you're gonna make or check whether 7 has a right part or not. So if 7 doesn't have a right part, do the threading. And in this case, if 4 did not have a right part, we would have done the threading of 4 also, but here 4 has a right part, so we won't thread 4, so we will thread 7 because 7 doesn't have a right part. This is the first destination and this is the second destination, and upon reaching each such destination you're gonna pop from the queue. Like when you reached 4, you're gonna pop from the front of the queue, and when you reach 7 you're gonna again pop from the queue. So now you're left with 6 to 513, and 6, that is the front of the queue, is the node that you want 7 to get linked to it. So remember, in order to do the threading, you must have, or I should say you must look at the front of the queue, and whatever is at the front of the queue, that will be used to do the threading. So now we are using the queue concept, that is we are popping from the front, and earlier we had inserted in the right. So pushing and popping are happening from the opposite side. That's why I have called this a queue. Now let's reach to the first destination, that is 4. So first in this code I'm going to check if a root is not none. In that case I'm going to reach 4 by recursively calling its left part, which means when I reach at this function, it's gonna return its authority back to its upper caller function, and in this upper caller function I need to do the pop operation because we have reached the first destination. So I am gonna say q.pop and pop from the 0th index, that is the front of the queue. And after reaching the first destination, in order to reach the second destination you have to go to the subtree, and that we can do by recursively calling the right part, which means we come here. And now when we are here, the function reruns again, and this function gets called, and when we are at this function it's going to return its authority back to its upper caller function. And when we are at this function, you can see that we have finally reached at our destination 2, and here the pop operation takes place. That is, earlier 4 and 7 were present, but they get popped out, and 7 gets popped out in this step. And now when you have reached here, you're going to check if 7 also has its right part or not. That is automatically checked when the third part, this third line of the code gets executed. So here you can see that convert root.right, it's gonna again recursively call the function, and here you can see that it passes none as the parameter, which means again it's gonna return its authority back to here. So here when we reach back, we gonna do the threading. All right, so now we have to thread 7 to its in order successor that is present at the front of the queue. So now I am gonna write if root.right is none and the length of the queue is greater than 0. So you can understand this, and this you will understand later, because remember that we don't need to thread 3 because 3 doesn't have an in order successor, and this will ensure that. So now let's thread 7 to 6. So for that I will write root.right is equals to q0. So 7 gets threaded to 6, and after this threading is done, this function gets over and it returns its authority back to here. So in this upper caller function, it sees that it has executed this step, which means now it's time to pop from the queue. Therefore here 6 gets popped out, and now the third line runs, and this time again a function gets called and none is passed as the parameter because 6 right is none. So again the authority is gonna come back to 6, and when that happens, this if statement is gonna run and it will check if root.right is none, and then it's gonna link 6 to its in order successor. Now 6 in order successor is 2, which is the front of the queue, so 6 is gonna get linked to in this step. Therefore we finally get this connection. Now we are done with this function. Now this function turns its authority back to its upper caller function. Now in this upper caller function, it has executed up till this step, which means now this if statement will run, and when this if statement runs, first it sees that if root.right is none or not. So root.right is not none because force right is not none, something is present there. So this if statement doesn't get executed and the function gets over. Therefore now we are back to this function. Now in this function it sees that it has executed its left part. Now it's going to pop from the queue, and after that it's going to look at its right part. So first it pops from the queue, and then it recursively calls its right part, which is this. Now again in this right part the function runs from the beginning and it recursively calls its left part, which is none. So the third is going to come back to this function, and when it comes back to this function it's going to perform a pop operation, and 5 gets popped from the queue, and now it's gonna do the recursive calling of its right part, which is again none, which means the 30 is again going to come back to this function, and now it's going to perform the threading operation because 5's right is none. So when the if statement executes, it sees that alright, 5's right is none, and also the length of the queue is greater than 0, which means thread it. Therefore 5 gets threaded to its in-order successor, that is 1. And now when this is done, we are done with this function. So this function returns its authority back to this function, and in this function now it sees that it has executed its left part, which means now it pops from the queue, and then it's gonna call. So first it pops from the queue, and then it's gonna call its right part, which is this function. And at this function same thing happened with 5, that is its right part and left part gets called, but both of those functions have parameters none, which means they hand over the authority back to this function. And also remember that when at this function the left part gets executed, that is this line gets executed, after that the pop operation happens, which means that 3 gets popped from the queue, and now the queue is empty, which means after the right operation is also happened, so after that this line runs, which means the right part is also called and it hands authority back to this function, and after that this if statement executes, and here you can see that 3's right is none, but this condition gets violated, which means it stops the threading of 3, and that is what we wanted. And after that the execution comes back to this function, and this function sees that it has done with itself, which means the entire function execution gets over, and we have finally threaded the binary tree. Now let's call the in-order queue function and the convert function in the main and pass root as the parameter. And before running this code, let's do these 3 print statements. That is, this first print statement should return 1, and this is going to return 2, and this is going to return 6. So here we go. So first we see that yes, it did return 1, 2 and 6. That is root.left.right.right.data is 1. You can see it here, root.left.right.right.data is 1. Similarly, root.left.left.right.right data is 2, and root.left.left.right.left.right.data is 6. And we have confirmed our threading is successful. So this is how we do the threading. I hope that you understood this tutorial, and like and share this video and subscribe to the channel.